Sorry for the slight delay. It's funny, but it's not funny. We live in a very honest campus. I panicked about 10 minutes before class because I couldn't find my little magic connector that connects my computer to the projector. So I brought a whole backup system here with me. We were going to use chalk on the board, but when I walked up to the podium, there it was from Wednesday. So you live in an honest campus. All right, so we're going to pick up on base nets. I guess one announcement before we get started. We are having a midterm next Monday. I think you know that if you've been tracking the schedule for the class. It will be a closed book exam. However, you're allowed to bring with you one piece of 8.5 by 11 paper written in as small a font as you care to write in on both sides, and yes, you are allowed to bring a magnifying glass. So my advice is it's a great way to study for an exam, to digest the material from the semester and try to boil it down to one page. And so I encourage you to do that. The class, the exam will be in class. It'll be 80 minutes. So be sure you're here on time. And there's really not much else to say. Any questions about that?
How many pages?
Pardon me?
How many pages?
How many pages? 400? No, we don't know yet. There'll be 5 16-minute questions, which adds up to 80 minutes. And each question will be worth 16 points. So it'll be easy for you to budget your time. That's part of the design of the exam. And it'll cover everything that we've covered through the semester with a focus on the things that we think are most important. And if you've been coming to class, I'm sure you know which things we think are most important. Yes?
When you said 5 problems, is it like assignment problems in which there are smaller problems?
Oh yeah, these won't, it won't just be 5 true or false questions. There'll be some structure to each question, yeah, with subparts, with subpoints. Okay? All right, so let's move on with base nets. Okay, so we looked at this last time, and as we discussed, a base net is simply a notation for representing joint probability distributions over collections of variables. In this case, here are 5 random variables. These happen to be Boolean valued random variables. And so the base net here is a directed acyclic graph among those variables, plus for each variable, a definition of its conditional probability given its immediate parents. In this case, the immediate parents of windsurf are lightning and rain. And so you can see for the 4 possible values that lightning and rain can take on as a pair, here are the probabilities of windsurf being true or false. So for a base net, to have a well-defined base net, all we have to do is write down the directed acyclic graph, and for each random variable, describe its conditional probability in terms of its immediate parents. And as we talked about last time, this is a way of specifying a collection of conditional independence assumptions. So I'm going to, so one of the first questions we could ask is how do we do, given a base net, suppose we're interested in the probability of some particular joint assignment of variables, then how can we calculate that given the base net? Well, it turns out to be amazingly easy. Does anybody remember what factorization of the joint probability distribution on the variables is implied by this graph? Remember, it's just, in general, this is saying that, oh no, we're going to get in trouble. Somewhere on this computer is the thing that I touch to turn it into a pen, but it's invisible. I apologize. Ah, it just appeared. See if that worked. Okay, we've got to a laser pointer. Okay. I need to do what? Enable editing, thank you. Oh, this is protected, thank you. Yes, there's hope. Okay, we're back. I apologize. Okay, so remember the joint distribution for a collection of random variables, we just write down the product for each of the variables of its probability given its parents, right? So in this case, if I just use the first letter of each word to represent the variable and so forth, then the joint probability of this is just, well, that'd be the probability that S equals 1, because it has no parents, times the probability that L equals 0, given what? S equals 1, times the probability of R equals 1, given S equals 1, times the probability of what I still need thunder here. Thunder equals 0, given L equals 0, times what? What's the remaining one? W equals 1 given, right, its two immediate parents. So this is really easy to calculate, right? These things turn out to be exactly the entries in our table. So, for example, here's the table for windsurf. We can look up the probability that windsurf equals 1 given this. What is it? .2, right? It's just, damn. Okay? Okay, so doing inference of joint assignments, this is just the probability of the windsurf equals 1, given that not L equals 0, and R equals 1. There's 0.2 in that table. So all we have to do, if we want to have a joint assignment and get its probability, is look up 5 numbers in the table here and multiply them. So computationally, this is incredibly efficient. So inference of joint assignments with a Bayes net is very efficient. In fact, learning in Bayes nets is very easy. You already know how to do it. Suppose that I give you this Bayes net, but I don't give you the conditional probability tables. And instead, I give you a set of training data where I list for each of the 5 variables examples. Right? Joint assignment of all 5 variables. Each training example is some observed day where the true or false values of those 5 variables occurs. How would you train it?
One way is using MAD. Basically, we are saying that, for example, a storm cloud, how many 0 and 1 we have. This is the probability of just a storm cloud, and the probability of just having a storm cloud. And then we can look at, for example, the cases that we have a storm cloud is 1, and then we have like how many, what is the percentage of having like if a storm cloud is equal to 1 and so on.
Perfect. So that's exactly right. All we have to do to train it is exactly what we did to train naive Bayes. Right? We could use, say, maximum likelihood estimates. We take our table. These are the parameters we know that we have to estimate, but we already know how to estimate the probability of windsurf being true given, I don't know, not L and not R. That's just a matter of collecting all the training examples where not L and not R happen to be the case and seeing what fraction of them have windsurf be true. That's our maximum likelihood estimate. Same way we train naive Bayes. Unless we decide to go with a map estimate, which we could do here too. So training Bayes nets is easy, provided we have the right kind of data, which is observed values for all these random variables, and provided somebody gives us the graph, just like they gave us the conditional independence assumptions of naive Bayes. So you can see how this is a very, very useful algorithm. You already know from having trained naive Bayes how to train these things, and you can see how easy it is to do the joint inference too. So you can make up a Bayes net if you have a data set. You can make up a Bayes net where you get to design what conditional independencies show up, and then train it, and then do inference on it. Okay, so in fact, in general, if you want to build a Bayes net, all you have to do is decide what variables you're going to use, and for each of those variables then, add it to the network, decide what parents you're going to give it, and then that, as we talked about last time, allows us to take what would have been the assumption-free factorization of the joint distribution that we get from the chain rule of probability and replace it by this more efficient product over the same set of n variables, but now where each term expresses some kind of conditional independence assumptions. Okay. So let's take an example, a winter example. Suppose I tell you that I want to build a Bayes net for medical diagnosis, and I know that bird flu and allergies both cause nasal problems, and that nasal problems cause sneezes and headaches. Then how would you build a Bayes net out of this? So first we'll have to make up some random variables, right? So here it's pretty clear that it would be wise for us to call this one bird flu, maybe this one A, this one N, this one S, and this one H. I could make each of these a Boolean variable, or I could make them continuous. In this case, I think it kind of makes sense to make them all Boolean variables. It'll make our life easier too. And then, what should I write down for the directed acyclic graph? Good. So according to that first sentence, bird flu and allergies cause nasal problems, and nasal problems cause sneezes and headaches. Good. So we can do that, and now if we have a set of training data, we could learn the conditional probability distributions associated with each of those 5 variables, and now we've got a Bayes net. Now, the question came up last lecture about what's the relationship between causality and these arrows that we're drawing? And I answered last time that just because an arrow is there, we can't necessarily say that it's causality. But in fact, I here came at it from the other direction. If I know that bird flu and allergies do in fact cause nasal problems, then I can certainly write this down. The arrow, in fact, simply means there's a probabilistic dependence between those 2 variables. They're not independent. Okay? So that's how you design a Bayes net. Now let me test your Bayes net prowess. Suppose I have 4 random variables, x1 through x4, with no conditional independencies. What does the Bayes net look like for that? Pardon me? Completely connected graph. I think that's impossible to build a directed acyclic graph that's completely connected. We need a directed acyclic graph that reflects no conditional independencies. I heard something up here. I'm sorry. Right, they are all connected, but here's one way to think of it. If I just use the chain rule and I wrote down this, what would the chain rule tell me? Well, it would say I can pick these variables in any sequence that I want, but suppose I do left to right, then it would say, well, it's p of x1 times p of x2 given x1 times p of x3 given x1 and x2 times p of x4 given x1, x2, x3. Right? That's just the chain rule, no conditional independence assumption. But what's the there's the factorization. What's the corresponding Bayes net that would have those 4 conditional probability distributions associated with it?
Straight line.
Well, it's not quite a straight line, so I'm going to draw x1 as a variable, and then x2 depends on x1, so I have to draw it this way. And now I can draw x3. Let's see, x3 depends on both x1 and x2, so I have to draw it depending on both x1 and x2. And then x4 depends on those other 3, so I have to draw it this way. Good. So here's a Bayes net, which if I wrote down the conditional probability tables for each of those 4 variables, I'd have exactly this factorization. Is that unique? No. Right? I could write down, I could have instead started left to right. I could have gone right to left when I wrote down the chain rule. And so then that first node would have been x4, and then x3, and then x2, and x1. Or, I got it backwards, but you see what I mean. Right? The chain rule says you can do this in any way you like. So I could, for example, do x3, and then the probability of x2 given x3, and then the probability of x4 given x2 and x3 times the probability of x1 given x2, x3, x4. These are just, you know, the chain rule says you can factor it any way you like. Each of those will give us, correspond to a different directed acyclic graph. Okay, so what you should be understanding here is that there's a direct one-to-one mapping between how we're going to express the joint distribution as the product of different terms, in fact, n terms given n random variables. There's a one-to-one correspondence between that factorization and the graph that we're writing. And of course, if we decide to leave out one of those variables because we believe there's a conditional independence, then we get to leave out one of the edges. I'm sorry, when I say leave it out, I don't mean leave out the whole term. I mean, for example, we could say, oh, but x4 is not dependent on x2. Then we could, okay, but for posterity, I'm going to leave it in there. Okay. Okay, good. What's the Bayes network for naive Bayes? It makes conditional independence assumptions. So suppose that I have random variables y, x1, x2, and the x3, and I'm trying to train a Bayes net or a naive Bayes classifier to predict y from x1, x2, and x3. Y has arrows into x1, x2, and x3. That's okay. What are the conditional independence assumptions that naive Bayes makes again? Right. It's assuming that xi is independent, sometimes you write independent that way, of xj given y. For all ij, for all I not equal to j. Right? It assumes all the xi's are conditionally independent given y. And what do we have here? Remember our rule that said every variable is conditionally independent of its non-descendants given its immediate parent. So here we have x1 is conditionally independent of its non-descendants, 2 and 3, given its immediate parent y. Perfect, right? That's saying x1 is conditionally independent of x2 given y. It's also conditionally independent of x3 given y. So that's right. That's exactly the set of conditional independence assumptions. And what's the joint distribution of this given this Bayes net? Well, it's just what we would have said before, p of y times p of x1 given y, p of x2 given y, p of x3. But with naive Bayes, we wanted to solve for P of y given x1, x2, x3, right? Like we wanted to know things like what's the probability that y equals 1 given that x1 is A and x2 is B and x3 is C. Remember that? That's what we were trying to do with naive Bayes. So how would we use this Bayes net and what we know about? Remember, we just talked about how easy it is to calculate the joint probability assignment. Like, it would be really easy with 4 multiplies to compute this y equals 1 and x1 equals A and x2 equals B and x3 equals C. That's something we can compute really easy, right? This is what we just talked about. All we have to do is look up the 4. There's our factorization. We just need to look up the 4 terms in those conditional probability tables, multiply them together, and we can get this easily. How do we get this?
Divided by P of y equals to 1.
Right. Right. So this, remember the definition of conditional probability? You should. This is just this divided by itself plus what? Right, plus the same thing, but with y, assuming y equals 0 instead. We're going to marginalize out y. Cool. Okay, so that quantity is P of y given the x's. Right, that's just the definition of conditional probability. It's just the probability of this joint thing over the probability of just that, which is just the sum of the case where y equals 0 and y equals 1. Good, so now you get to see that we can also use Bayes nets not just to easily calculate joint probability assignments, but if we're interested in conditional probabilities, one way we can get that is to calculate the associated joint probability assignments and then do the right algebra to get the conditional distribution we're interested in. And this one's pretty inexpensive too. Remember, it only took us 1, 2, 3, 4 multiplies to get the joint thing here. And so now we have to do that twice. This is the same as this, so we have to calculate this. So it's 8 multiplies plus a divide and a sum. It's not a big deal. If this in general, the problems get to be arbitrarily complicated. If you have a big net and you're trying to get the conditional probability of x1 and x3 and x5 and x7 given x2 and x4 and x8 and x10 and x11 through 12,000, then it gets to be expensive. But you see the flexibility that we have. Here's a baseline approach to calculating any conditional term we're interested in. And we're simply going back to the very first thing we said about the joint distribution. Remember, I was so excited about how awesome the joint distribution is. The reason is, once you've got it, you can calculate anything. And all I'm doing here is going back to that very same baseline approach. BayesNet gives me a simple way to calculate joint assignments for any probabilities of any joint assignment. And so once I have that, I can combine those in different ways to get any conditional or marginal distribution I want. When I say marginal distribution, by the way, I just mean leaving out some of these variables. Like what is P of y equals 1? Oh, that's a good one. What is P of y equals 1? In naive Bayes, we wrote that down as an explicit parameter. How would we calculate P of y equals 1 from this Bayes net?
One thing is we can say we can have two values for x1, two values for x2, and two values for x3. So we have 8 different cases that will relate to one y equal 1.
Right, right. So we could just sum up all the joint assignments where y equals 1. And there are 8 possibilities. So we could calculate those and sum them up. Anybody see a cheaper way to do it? I can do it without any multiplies. Let me ask you, what's the conditional table that we associate for this? The conditional probability distribution tells me the value of given the parents, tells me the value that x3 equals 1 and x3 equals 0. And that's conditioned on what for x3? Conditioned on y. So I have to condition on y equals 1, y equals 0. And so I'll have some terms in here, right? But what's the conditional probability table for this one? Has no parents. So the only thing we need is, this is just P of y equals 1. So it's sitting there. It turns out P of y equals 1 is one of the parameters that is in one of the 4 conditional distributions that we've already written down. See what I mean? It's like, what if I asked you, oh, what's the probability of x3 being 1 given that y equals 0? Well, we just read it off this table. We wouldn't have to sum up over all the joint assignments and average them out. So now you see another approach to doing inference in Bayes nets. Sometimes, well, think of it this way. Excuse me. The baseline approach is reduce it to sums and multiplies and divides over probabilities of entire joint assignments of all the variables. You can always do that. And then approach 2 is sometimes you can get away by just using and manipulating the particular conditional probabilities that are actually stored explicitly in the conditional probability distributions for each of the nodes. And it's kind of tedious, but if you have a big Bayes net, sometimes it's worth investing some energy to see if you can come up with a more efficient algorithm that uses some of these stored parameters that are in the distribution, in these conditional distributions. Because those you do have, that's what you had to estimate to learn the Bayes net in the first place. And that's what you're using in order to multiply together to get these joint assignments. All right? Is that clear? Okay, good. Here's kind of an interesting question. What if we have a more complicated Bayes net? Here's one that talks about automobiles and whether they're going to start and how that relates to things like have the condition of the fuel pump and the distributor and the spark plugs and stuff. What if some of these random variables are discrete, Boolean even, like either the car starts or it doesn't start? But some others might be continuous variables, like, oh, the one up in the top right is battery age. So that might be a continuous variable. So in that case, how do we build Bayes nets that combine discrete and continuous variables?
Can you set a threshold and make them binary?
Right, you're saying, well, we may have to threshold something on the continuous thing. But in general, what we have to do is just the same thing we talked about. A Bayes net is a directed acyclic graph, there's one, plus for each variable here, a representation of the conditional probability of that variable given its immediate parents. And so if everything is a Boolean variable, we just use a Bernoulli distribution. It's very easy. But if some of these are conditional, are continuous, then we might pick a different form of distribution. So for example, battery age influences the battery state. Maybe we decide to call battery state a Boolean thing, good or bad, and maybe battery age is continuous. So in that case, we could, for example, make up a probabilistic dependence of the Boolean battery state on the continuous battery age, for example, by saying that, well, you could do it a lot of ways. We could make a monotonically decreasing probability distribution with battery age and say that's the probability that the battery state equals 1. So in general, we can still do it. There's nothing magic about, we don't have to require that every variable in the Bayes net be Boolean. You can have mixes and matches of n-ary values, Boolean values, continuous values. But when we do, we have to also make the design choice of what form of probability distribution are we going to use for each one of the required conditional probability distributions. Okay. How many people here have heard of hidden Markov models? Good. We're going to spend a little bit more time on them later on in the semester, but I just want to point out that a hidden Markov model is just a Bayes net. Bayes nets are a very general framework for thinking about things. A hidden Markov model is actually a probabilistic model of time series data. So in this particular one, I filled in these random variables to indicate that they're observed. This might be some observed time series, like, I don't know, how tired you are when you wake up on day t or t+1 and so forth. And in a hidden Markov model, we assume that that observed data is due to some hidden latent sequence of states that's not directly observed, but that, like for example, you might be, S here might be whether you're healthy or have the bird flu. And given that, you might wake up, in one of these states, and there will be, in the hidden Markov model, some dependence of how healthy you are on day t+1, given how healthy you were on day t. But again, we can model these things as simply a Bayes net. And in this case, notice that when we go to train it, we can't use the simple strategy that we talked about before of maximum likelihood estimates for everything, because only some of the random variables, the greened in ones, are observed. And if we don't observe the white ones during training, then we have to use a more complicated learning algorithm. And we'll talk about that. Okay, so the final thing that I really want to do today is come back and revisit the idea of conditional independence in Bayes nets. So hopefully by now you're convinced, as I am, that Bayes nets are a very general purpose framework for representing probabilistic models that we might want to learn. And we did start our discussion of Bayes nets by pointing out that one thing is true, is that a variable is conditionally independent of its non-descendants given its immediate parents. But I also mentioned in passing when we pointed that out that that's a sufficient condition for being conditionally independent, but it's not a necessary condition. That doesn't cover every case. So I want to come back and cover every case. So it turns out, for example, we can say that x1 and x4 are conditionally independent given x2 and x3. And it's not quite clear, it's not clear from the original rule that we gave that that would necessarily be the case. So let's take a look at how we can have a complete way of enumerating all of the conditional independences in a Bayes net. Okay, so it turns out that the answer is a property of graphs called d-separation, and we'll define it in a few slides. But the d-separation between two variables in a Bayes net determines whether those variables are conditionally independent given some third set of variables. And it's built to define it. We're going to build it out of three basic cases. And here's the first of them, a simple case. So if I ask you, is A conditionally independent of B given C, you would answer yes, because it's even, that's given by the rule we said. A is conditionally independent of B given C. Well, a variable is conditionally independent of its non-descendants given its immediate parent. Therefore, B is conditionally independent of A given C. And because conditional independence is symmetric, it is symmetric, right? That would have been a good midterm question. It's trivial to see why it's symmetric, right? The definition of conditional independence, oh man, is if X is independent of Y given Z, that means that the probability of X given Y and Z wait a minute. I could write it that way. Is the probability of X given Z, which implies that the probability of Y given X and Z equals that. But I guess you'd have to prove it the way I wrote it down there. It would be a good thing to, it's a good practice. We won't put that on the midterm, but it's a great question for you to work on while you're studying for the midterm. Okay, but let's prove this one. Let's prove that A is conditionally independent of B given C. I'm going to pull out my... So again, if we want to prove this, all we have to do is write down the definition of conditional independence, right? So we're trying to prove let's say if A is A and B given C, if those are conditionally independent, that means this equals the probability of A given C times the probability of B given C. Right? That's what conditional independence means. So if I say is conditionally independent of B given C, it means that. Right? Their joint distribution is just the product of the two. That's what we did in naive Bayes. You said the probability of x1 and x2 given y is just the probability of x1 given y and x2 given y. Actually, from there, you can see why it's symmetric. Okay, so now, according to this Bayes net, though, let's write down, we want to prove that this is true for this particular Bayes net. So what should I write down if I want to write down that conditional probability? Well, let's start again with the definition. Probability of A, B given C. And here, by the way, I'm using little letters. Here's a convention we'll use a lot. When I mean the probability that uppercase A random variable takes on the value little a, I will sometimes write this as okay. And similarly, I'll write probability of little b, meaning that the random variable uppercase b takes on the value little b. It just saves us a little. So here, what this really means is the probability that uppercase random variable a takes on the value little a, and uppercase random variable b takes on the value little b, given that uppercase c takes on the value little c. So what is that? Well, by the definition of conditional probability, that's just the probability of seeing A, B, and C over the probability of seeing A and B. Oops. C. Okay, and now, given that Bayes net, how can I rewrite the numerator? How can I rewrite the numerator? Right, it's the usual factorization. I start at the root, A. It has no parents, so all I need is PA. And then P C given A. And then P of B given C. Again, the Bayes net tells me I can factor the joint distribution that way. And so it's this. Oh, this is cool. Look at this part. That's just, that's the chain rule, right? On the top there, I can re-express that as P of A and C over P of C, right? By the chain rule. And that's the definition of P of A given C. So this whole expression is P of A given C times P of B given C, which is what I was trying to prove. Okay? So these, these kind of simple manipulations of probability are things that you should, by now, be pretty comfortable doing yourselves. We really only use a couple rules when we do these things. We use definitions of conditional probability, definitions of conditional independence. We use the chain rule. We use the fact that some probabilities have to sum to 1. And that's about it. Oh, we use Bayes' rule. And you know each of those things. And so for a lot of questions that you might encounter, like this one, you actually are equipped to reason it through and come up with the answer. Okay, so we just proved, basically from the definition of conditional probability, plus the definition of how Bayes nets represent joint distributions, that if we have that particular graph, then it implies that box thing at the top. That A and B, the probability of A and B given C equals the probability of A given C times probability of B given C. A and B are conditionally independent given C if we have that Bayes net. Okay, here's another one. What about this one? I'm looking at the clock. I'm going to skip this one and let you do this one. Okay? But it's just as easy as the one we just did. Here's another one we could do. These are the 3 cases out of which we're going to build our these are cases out of which we're building the definition of D-separation. So one is this simple triangle network where the arrows, one arrow leads into C and one leads out. A second one is where both arrows are going out of C. In fact, if you look at that sideways, it's exactly what you already told me is the naive Bayes net, where C here would play the role of Y, and A and B would be X1 and X2. You already told me that was the graph for a Bayes net, and so if you were right, then that does mean that A and B have to be conditionally independent given C. Yep?
If it's any complex Bayes net model is there, and there is no variable observed, then everything is connected, right? So there is no independence.
Well, oh, you mean if there's an edge for every pair of variables?
As in that there is no variable that is being observed. Like in this case, we have given C.
Oh, if no variables are observed.
Then everything is connected and there is no conditional independence.
Well, when we talk about conditional independence, what we really mean is when we say that A is conditionally independent of B given C, what we mean is if we observe the value of C, then A and B are coupled. And if we observe nothing, then it doesn't even make sense to talk about conditional independence. Right? Okay, and here's the third one where instead of the arrows coming out of C as they do in the naive Bayes case, in this one they're both going into C. And here, is it true that A and B are conditionally independent given C? No, it's actually not true in this case. But interestingly, it turns out to be true that A and B are marginally independent. That is, so the answer to this is no. It's false. But the probability of A and B is the probability of A times the probability of B. As long as C is not in there. And although it's not true, right, P of A and B given C does not equal P of A given C, and P of B given C. So this gets to your question about whether things are observed or not. So what this shows is that we can have a situation like this where A and B are not conditionally independent given the value of C. However, if C is unknown, and we just ask for the joint probability of A and B, which of course means we're marginalizing out C. We're summing up over the case where C equals 1 and C equals 0 weighted by their respective probabilities. Then it is true that P of AB factors this way. And let's prove this one. It's actually not hard. So, oops. To do this, all I have to do is notice that P of A and B is just the sum of P of A equals A, B equals B. I'll write it out this way just to be clear. C equals 0 plus the probability that A equals little a, B equals little b, and C equals 1. That's what we mean by the probability of A and B. It means the sum of those two rows in our joint probability table. But this one we can factor these. So now that we've got this Bayes net, we can say, well, this factors into what? Well, this is the probability of A, the root here, times the probability of B here, and then C given A and B. Right, plus but that's the same as that's just a sum, so I can keep the PAB outside the sum and then just say it's the probability of C equals 0 given AB plus the probability of C equals 1 given A and B. And this quantity, of course, has to be 1. C can only be one of those two values. And so there's our proof. Okay, so this proof shows, first of all, just kind of reminds us what we mean when we talk about a subset of the random variables. It doesn't mean that they don't exist. It just means they exist and we don't know their values. So C still exists when we talk about P of A and B. It's just that we don't know its value, and so if we want to prove, as we did here, that P of A, B equals this, we have to take C into account and all of its possible values weighted by their probabilities. But in this case, the good news is they just kind of disappear into this term becomes a 1. Okay, so now you see this is the sense in which A and B are independent. We call that marginal independence, despite the fact that they're not conditionally independent given C. Okay. All right, so now we're ready. I'm going to pass that. Now we're ready to talk about D-separation. So D-separation is the rule that's complete, necessary, and sufficient for determining conditional independence in a Bayes net. And here it is. Let's just read it first. We'll say X and Y are conditionally independent given Z if and only if X and Y are D-separated by Z and X and Y are D-separated if every path from X to Y is blocked. And now we're generalizing our definition, by the way. X, Y, and Z don't have to be single random variables. They can be sets of random variables. But to illustrate, let's look at it this way. We'll say that a path is blocked. There are two ways it can be blocked. One is that Z can block a path that has to go through, if X and Y have to go through this path, and Z is the thing we're conditioning on. Right, we have X, Y, and Z, and X and Y appear somewhere in this Bayes net. But to get from X to Y, we have a path that goes like this. Then Z, the one we're conditioning on, blocks this path. And similarly this. So if it's either the head coming in and the tail going out, or two tails going out, Z blocks it. But as we just saw in the previous slide, it's not the case that if the two arrows come into Z, that A and B would be conditionally independent. That's what we just proved. We just proved, well, we didn't prove that. We proved that A and B are still marginally independent, but they're not conditionally independent. Okay, so that's the easy case. The one that's a little more subtle to get your head around is that in addition, a path is blocked for the question of are X and Y conditionally independent given Z. If they have to go through a path which does not involve Z, but where the arrows meet head to head, and neither that node nor any of its descendants are in Z. Okay, so that's a little bit tricky to look at, but let's look at a few examples. So let me ask you this question. Is X1 in this Bayes net independent, conditionally independent of X3 given X2? Who thinks yes? Who thinks no? Okay, the yeses are right. Why? Somebody want to tell me why X1 is independent of X3 given X2? Don't be shy. Well, for one thing, node is, our original definition actually covers this one. X3 is conditionally independent of X2, or of its non-descendants, including X1, given its immediate parent X2. But also, this is one of the paths that gets blocked. In this case, X2, because we're conditioning on it, blocks the path from X1 to X3. It's the only path that there is, and so it's this pattern. Okay, is X3 independent of X1 given X2? Yes, by symmetry. Conditional independence is symmetric. Is X4 independent of X1 given X2? Yes. Again, X2 is observed, so the only path from X1 to X4 goes through it, and it's exactly this type of node, so it blocks it. Okay, let's ask a couple more tricky ones. What about X4? Is it independent of X1 given X3? No. So again, there's only one path between X4 and X1. You can see the two nodes it goes through. And X3 in this case is given. So neither of those top two patterns, this is two heads, two arrows coming in. That's neither of those two patterns, so we can't use that excuse. Could we use this one? No, because we don't have any. The only node with 2 arrows coming in is actually our observed, the one we're conditioning on, x3. And so we can't use excuse number 2 either. Okay? So that's a no. What about the second question? Is x4 independent of x1 given both x3 and x2? Yes, because now, given x3 and x2, well, x2 suddenly satisfies that first thing. A and B there do not have to be outside of Z. They can be inside of Z. Okay, so that one's a yes. What about the final question? Is x4 marginally independent of x1, given nothing? It is then, right? Because now we block it this way. We're given nothing. We don't know x3. And so this is sufficient to block the path between x1 and x4. So this d-separation lets us read off marginal independence as well as conditional independence. Marginal independence is just the special case where we condition on nothing. And in that case, of course, rule number 1 won't help us, but rule number 2 tells us that things can be independent. The other way they can be independent is if there's no path at all between them. Yes?
So this is like x1 and x4 are derived from different sources, when x2 and x3 are not given, so they are independent just because they are taken from different sources.
No, they're not.
Because they are not connected to anything.
Oh,
They are not connected to anything.
that's good. So the question, if you didn't hear it, was, are x1 and x4 independent just because they're taken from different sources? I'm not quite sure what it means that they're taken from different sources.
In the sense that they're not connected to each other and they're not getting that information from somewhere else or other nodes. They are separate. They're not really same.
So in this case, I believe they are. These are independent. But it's justified by this rule, where this guy gets to be C. Now I could write another, if I did this one. Think of this Bayes net. Again, with nothing observed, and I ask, is x1 independent of x4? No. So in a naive Bayes classifier, the x sub i's and the x sub j's are not independent. They're only conditionally independent given the label. Yes?
But that rule still holds, like what she told, it still holds because x1 and x4, they are coming from a distribution that is defined by y. So
That's
that is why
right.
They are not independent.
Yeah, that's good. That's right. So if I have two random, maybe one way to get at what you're saying is if I have two random variables that have no parents, then you're saying they must be marginally independent. And I think that's right, because I think there's no other way to complete the graph, even leaving out an edge so that they're just disconnected components, then they'll be independent because there's no path. If there is a path, then the fact that they both have outgoing arrows, if there is a path, means there must be some node that has two arrows coming in. And then that'll automatically allow this to block it. So that's good. Wow, that's good observation. I had never thought about it that way. Okay, so this takes a little bit of practice, and you'll get a little in the homework, which is due Wednesday, to look at these things and get some practice using this rule, this D-separation rule, to read off independence. But I think this is probably a good, there are a couple more examples in today's slides. The other final definition I want to give you, this is kind of useful, is what's called the Markov blanket of a variable in a base net. And here's the definition. The Markov blanket of a node X comprises the set of its immediate parents, its immediate children, and its co-parents, meaning the immediate parents of its children. And this Markov blanket, which in this case includes these 6 nodes, has the property that the conditional distribution of xi, given its Markov blanket, is independent of everything else in the network. So this is kind of like the Markov blanket is the thing that isolates a node from all the other nodes in a network. So this is a useful notion, especially if you have to do inference on a big base net. If you can identify its Markov blanket, that's often very helpful. Especially if you can observe all the variables in the Markov blanket, then you can just ignore everything else. Now you might have thought we didn't need these nodes. But you know we do, because remember our D-separation rule, which told whether, for example, a node can be independent of another node or conditionally independent. That didn't allow this case with the 2 arrows going in to block the connection. One way to think about this, an example that I think I got from Stuart Russell, was that imagine this is the alarm goes off in your house, the motion sensor. And this is a burglar just entered your house. And this is, you just had an earthquake in your house. And so you can see that if the alarm goes off, you might think they have an earthquake. But if you know whether or not there's a burglar in your house, that gives you a lot of information. Right? If you know that there's a burglar in your house, it's much more likely that you're having an earthquake. So that's a nice intuitive example about how this value kind of explains away what would otherwise be the need for xi to explain why the alarm is going off. All right, so that completes, you now actually know everything there is to know except for things that follow from this about directed base nets. And we're going to use these some more in the semester, but it's really a very powerful thing. You can see that it subsumes naive Bayes. When we introduced that, it was just really a special case of this. And it's one of the more practical and useful ways of building probabilistic learning algorithms. Okay, so don't forget homework is due Wednesday, and I'll see you then.